Alright, in this one I want to prove that the derivative with respect to x of the function e to the x is equivalent to itself. Yeah, so this is equivalent to e to the x, which is, very, very interesting, right? Because it's, as far as I'm concerned, it's the only function that that's derivative is itself besides zero, right? But zero is obviously, it's not that surprising. So, but yeah, any point on this graph um, has an instantaneous slope of e to the x, right? And that is quite, interesting. So I'd like to prove this actually. So the way I'm going to look at it is with the limit definition. So we said that dy dx, small change in x and its resulting change in y, is equivalent to the limit as h approaches 0 of f of x plus h minus f of x, and that's all over h. So the next line would be, well, we kind of need to plug in e dx, right? So limit as h approaches 0, and the way you would do it is you do e to the x plus h, and then you subtract the original function e to the x, and then that's obviously all over h. So the next thing we could do is separate the e to the x plus h. So in algebra, you would have learned that if you have two xy times xz, you can simply just, and if they're, so you have two exponents that are multiplied together with the same base, you can simply just add the exponents, so y plus z in this case. Well, in this case, e to the x plus h, we can separate it out, right? We could do the opposite. So in this case, it would be limit as h approaches 0 of e to the x times e to the h minus e to the x, and that's all over h. Next thing, we can we're not taking, well, first of all, let's factor out the e to the x, right? In the numerator, there's e to the x that in this term and then the second term, so we can factor it out and it would become e to the x times e to the h minus 1, and that is all over h. So now we can see we're not taking the limit of x, so we can just bring this out here, right? So it would be equal to e to the x, limit as h approaches 0, of e to the h minus 1 all over h. So now this is the interesting part about this part. So the problem we face is that, well, the ultimate goal of trying to rearrange and do all that stuff was try to get rid of this h, right? Because, if we divide by 0, obviously you get an undefined fraction. Or, yeah, just undefined. So somehow we kind of need to do something to get rid of this. So there's something called L'Hopital's rule, and essentially it says that you take the derivative of the, so if you have a limit of some function, the equivalent limit would be f prime of x over g prime of x. See, now the problem with doing that is, well, it's kind of a circular logic, right? Because we're trying to prove that the derivative of e to the x is itself. So in this case, if we were to take the derivative of the top, we would have to make the assumption that e to the h is equivalent to e to the h. So, I mean, we can't really use that to prove it. So the other way is kind of like this. So you have a table. You have h values, and you have your output, which is your e to the h minus 1 all over h. And pretty much what you kind of do is you want to take really small numbers that are quite close to 0, but not at 0. So you would get a pretty close answer, but not, not 0, so that it wouldn't be undefined. So you could do like 0.0001, and you keep on doing this to more accurate digits, and you could do it from the right and the left, but it all approaches this one answer. So if you take 6 digits, 1, 2, 3, 4, 5, 6, 0.000001, you get 1 as your output. So in other words, if I plug in a really small number that's close to 0 into this H and this H, I get 1. So, I mean, you can try this on your own and you should get the same answer. So yeah, this is all equal to 1 now. And that's kind of one of the most important parts of the proof. And once you get that, you can just, well, you just get e to the x times 1, and that's just equivalent to e to the x. So that kind of shows that the derivative of e to the x is indeed the function itself. So thank you for watching.